If you've ever driven along a winding mountain road, you've probably noticed huge concrete walls hugging the slopes, holding back tons of earth and rock. But have you ever wondered why these massive structures are there, silently performing such a critical role in our infrastructure? Because behind those walls lies a constant, unseen battle, a continuous tug-of-war between the relentless, downward force of gravity pulling the earth downwards and the precise, calculated engineering holding it firmly and securely in place. This delicate balance is crucial for safety. When a slope becomes too steep, gravity inevitably wins, overcoming the soil's natural resistance. The soil loses its inherent balance and begins to move, initiating what we know as landslides, which can be incredibly destructive. Flattening the slope can keep the soil calm and stable. But in many places where space is severely limited, such as along busy highways or in urban developments, we simply cannot create gentle, expansive slopes. Therefore, to manage these challenging terrains and protect lives and property, we construct robust retaining walls. These walls don't just stand there passively. They actively fight back against the invisible push of the soil. This unseen, powerful force is known as earth pressure, or more precisely, lateral earth pressure, because it acts sideways, directly on the wall, constantly testing its strength and stability. The magnitude of this pressure depends on many critical factors, including the specific type of soil, whether it's sandy, clayey, or a mix, its moisture content, which can significantly increase its weight and fluidity, the inherent stiffness of the wall itself, and whether adequate drainage is provided to relieve hydrostatic pressure. That's precisely why calculating earth pressure isn't straightforward. It's what engineers refer to as statically indeterminate, requiring complex analysis and careful consideration of all variables. However, a brilliant Scottish engineer named William John Macon Rankine found a revolutionary way to simplify this complex problem in the 1800s. He made some clever, foundational assumptions about soil behavior, such as assuming cohesionless soil and a smooth, vertical wall, and provided us with a simple yet powerful theory that is still widely used and respected today for its practical applications in geotechnical engineering. To truly understand Rankine's theory, imagine the soil behind a retaining wall as having three distinct moods or states, each corresponding to a different interaction with the wall. First, there's at-rest pressure, which occurs when the wall doesn't move at all, maintaining a static equilibrium. Second, we have active pressure, when the wall moves slightly away from the soil, allowing the soil to expand. And finally, there's passive pressure, when the wall pushes directly into the soil, compressing it significantly. When the wall is perfectly still and unmoving, the soil behind it remains in a state of perfect balance, exerting a steady, consistent force. There is no expansion, no compression, just a steady, consistent sideways pressure reflecting the natural state of the soil. This is precisely what we call the at-rest condition, a state of equilibrium where the soil is undisturbed by wall movement. Now, imagine the wall leaning back ever so slightly, moving away from the soil. The soil behind it begins to stretch and expand, attempting to follow this movement. Initially, it resists this change. But as the wall continues to move, the soil's inherent shear strength is eventually reached, and it fails, allowing it to deform. This is known as active earth pressure, representing the lowest possible pressure exerted on the wall, as the soil is in a state of minimum resistance. Conversely, imagine the wall now pushing directly into the soil, compressing it. The soil gets intensely compressed, pushing back with increasing force until it too reaches its failure point, where it can no longer resist the applied pressure and yields. This intense resistance is passive earth pressure, representing the maximum possible pressure the soil can exert, as it is in a state of maximum resistance and compression. Rankine utilized a clever visualization tool known as the Mohr's circle to precisely determine how stresses change within the soil with different types of movement and deformation. From this insightful graphical analysis, he derived two crucial constants, K and Kp, which are the coefficients of active and passive earth pressure, respectively, providing a simplified way to calculate these complex forces. In reality, soils are rarely perfect and uniform. They can be highly variable. They can be wet, cohesive, or have varying slopes, and their properties can change with depth. Walls can also be rough or smooth, significantly altering friction and pressure distribution between the soil and the wall. Therefore, engineers frequently modify Rankine's theory, incorporating additional factors and empirical data to accurately account for these diverse real-world conditions and ensure the structural integrity and long-term stability of retaining walls. So next time you drive through the hills and observe those imposing walls, remember, they are far more than just concrete barriers. They are silent guardians, born from intricate equations, fundamental physics, and centuries of accumulated engineering wisdom, meticulously designed and constructed to protect our vital infrastructure, prevent landslides, and ensure our safety on the roads. Your valuable support helps us continue turning complex ideas into engaging and informative stories worth watching, bringing engineering marvels to a wider audience.
Thank you for watching and supporting our content. We appreciate your engagement. For more videos, hit subscribe. Your subscription helps us create more content.